Welcome to this industrial keynote session by Intel. With me today, I have Jim Jeffers, who's going to talk about the arts of Intel's advanced ray tracing. My name is Felicia Lai Jakobsson, and I work at Visual Sweden, who supports innovation within visualization and image analysis. Jim is an Intel Senior Principal Engineer and also the Senior Director of Advanced Rendering and Visualization. He's been at Intel since 2008, and Jim was part of the HPC, High Performance Computing team, that developed and deployed Intel's many-core Xeon Phi products. He has co-authored 4 books on parallel programming, and in his prior work, he helped out developing the VFX technology behind embedded television graphics, such as the first electronics touchdown in American football. I am also very proud to let you know that Intel is one of the very generous companies that has made this conferences happen. It's with warm hands, I'm now leaving the stage over to Jim Jeffers.
Hi, everybody. Give me a second to set up and share my screen. It will take a second or so the way my system works, so just bear with me. Okay. Try that. And actually, I have to go all the way to the beginning. Okay, let's start there, and then bear with me 1 second while this happens. Okay, so as I get started, I first want to thank everybody for joining, and again, very pleased to be here virtually. I do miss my friends. I had late last year and early this year was looking forward to going to Sweden for the first time, but apparently that's not going to happen. But on behalf of Intel, I'd like to wish everyone please stay safe. Things are still not perfect, so please, as I said, I hope your families and everyone is doing well. Today I'm going to talk about, mostly ray tracing and rendering capability. I believe that every single image that you're going to see in my slides, other than things like this graphic here, or this here, are rendered with Intel One API Rendering Toolkit and one or in combination of our many libraries. I'm going to give you a quick overview. I don't want to bore you too much with going back over stuff you may already know from past years. And then Felicia will be taking questions if I go over anything too fast. So let's move on. Now let's move on. There we go. Oh, slow reaction. Okay. Just I'll be kind of as background information, be talking about this. This is one of the ways that we look at the rendering and visualization taxonomy, and all these, I guess you want to call them markets or domains, our toolkit touches, as well as other rendering capabilities across the industry, from final high quality rendering all the way to the left, where it's sometimes called offline. You often have minutes or for movies and films, you potentially have hours per frame as they try to get it to photoreal perfection. The process of actually creating that content is usually interactive, or only needs interactivity, and that's a core set in the middle. animation on workstations, scientific visualization from workstations all the way across the whole cluster, and then the very large CAD, CAE, CAM architectural design, and then gaming design, and then even gaming activity. Now, as you tend to move from left to right, you tend to see more and more performance desired and closer to real time. Today, although that's shifting rapidly, and we'll talk about that, that is using the tried and true long-term rasterization methodology. And then as you go to the left, it becomes almost 100% ray tracing. So just one way to look at it. And also, I'll be talking a bit about platforms. So if you look at the bottom of the screen, you'll see the platform affinity from high-end dual socket Xeon workstations and multi-node or many-node supercomputers, all the way over to PCs and consoles. But interestingly, that arena, again, we'll touch upon it, is also moving towards cloud as an option to provide a new set of access and new, actually, compute capability that you can't always get with your local computer. I recently wrote an article, so I just wanted to touch upon some of the concepts in there. It was called "One Size Does Not Fit All." So as you consider your use cases, your needs, your development, your research, these are the types of things that we are thinking about at Intel. So think about an open platform, not just a particular kind of compute device. Think about the scalability. Sometimes you need extremely high quality rendering, like on the Bentleys on the right. Yes, that is not a photograph. And then the flexibility to do everything from basic simple rendering like a Cornell box all the way up to things like in the lower right, the stellar radiation. We'll talk a little bit more about that later. So yes, for example, the Bentley image here is it's exactly 11 Bentley design models placed in a virtual showroom. That together has about 120 gigabyte footprint. So you really need your whole platform to work with it. And again, the scalability lets us use a multi-node environment to run this at upwards of 20 frames per second interactivity with denoising. And in this case, the thing behind it is Intel Osprey, which I'll talk more about. And then if you really want to go interesting and large, we've got the over 2 terabytes. Actually, it's a 7 terabyte data set. So even when we have a dual socket setup with 3 terabytes of Optane DIMMs, we even have to decimate, not decimate, but what we do is we take out time steps. But we're able to run 3,000 time steps animated and explorable. So these are the kinds of scale that you can get. Of course, you can also go all the way down to laptop scale, depending on the features and quality you want. I also want to point out, it's not on the slide, really good article from the chief scientist. It's a blog, actually, of Luxion. They have the key shot application and renderer. Forgive me, I know the first name is Henrik, but I really encourage you to read that. It's a great article on benchmarking and conceptually understanding the dramatic differences between CPU rendering and GPU rendering and how to look at those two. So it's very good. And from an Intel perspective, and I can either take questions on it or talk about it, as we look at ray tracing capability in our future XE platforms, our goal is to look at it from a platform perspective. So when you see, if you look at Henrik's article, you'll see that he's positioning the two against each other. What and when CPUs are good, when our GPUs are good. From an Intel perspective, we're looking at combining the two. A notion that Raja Kadori, our senior VP, calls no transistor left behind. So keep that in mind as we go forward here. Okay, and you know, a lot of people talk about mega trends, but you know, that's too tiny for me. So we are heading to exascale. So let's talk about Exa-Trends. Better and more better ray tracing for high performance computing, in situ rendering, and then something that I don't necessarily know a lot of people are aware of, but there's more and more utilizing ray tracing, which of course at its core is a physics algorithm for various types of actual compute, you know, in you know, as juxtaposed to visualization or in conjunction with visualization. So again, we have our friends at UC Santa Barbara and Argonne Labs utilizing ray tracing and have you know, used this data set from basic you know, rasterized or you know, ray traced volume rendering, to this case where our open volume kernel library now has the capability to do spherical. As you can see, it's a spherical volumetric path tracing to really get some stunning, not only stunning imagery, but the ability to really get the nuances when this is operating. I will actually post a video of the stellar radiation multiple time steps, a screen capture that we've done, so you can see the type of things scientists can do. We'll post that the next day or so. We also have the notion of in situ rendering, particularly in high performance computing. This is an example of Sensei with an Osprey backend rendering a LAMPS molecular dynamics application. And we are working closely with Argonne National Labs and the whole industry across the world on enabling what I call real-time or real-time turnaround compute and visualization, which dramatically reduces the I/O that you need on a system when you're working with terabytes and petabytes of data. So this is something that we're actively working on, and feel free to follow me and look at what's happening in situ. Another project is very cool that we are, again, exascale project called Vestec. It's a European Union project, and one of the driving applications is this solar, wind, and comic effects, sometimes called space weather, and the space weather can affect communication, satellites, you know, magnetic pulses from the sun that we're aware of. And again, a very large data set here. And we have demonstrated that this up to 650 gigabytes of data on a 192 gigabyte platform. In this case, a technology that maybe a lot of people aren't fully aware of, but our Intel Optane SSDs can be mapped as memory, very similar to our Optane DIMMs, and you can get some quite stunning results. And then finally, keep track of something called the Solar Ray Tracing Consortium. That is the use of ray tracing, in this case on the screen, Monte Carlo methods, for doing compute of various things. In this case, a cancer treatment simulation. More Exa-Trends, open standards. We, as you know, and we'll talk about it in a second, that our One API Rendering Toolkit is all open source software. We have found that this allows us to easily work across the industry. What's really cool is a new standard by Cronus called Inari is under development. Instead of the multiple potential backends, including Osprey, VizRTX from NVIDIA, Radeon Rays, and ProRender from AMD, Vulkan, even OpenGL. Today, because these, while many of the interfaces are open or able to be used, you've got to replicate your code and deal with the fact that they're all different capabilities. So Inari is bringing together industry applications. Many of the applications that you see here are participating in order to create a high-level screen graph-based interface in the vein of Osprey to the industry as a standard. So it'll be easier for you as developers and researchers to get access to different types of hardware and capability and ease your development. So keep an eye on this. Again, cross-industry, cross-vendor standard that we're very excited about. And then over in the film industry, which often is beginning to get utilized in scientific visualization, we are a founding and premier member of the Academy Software Foundation, and it continues to grow various projects, important projects, taking them or basically being offered them into the Academy Foundation to manage going forward. A very recent adder is open shading language, which is getting rapid adoption. And I can give you a hint that universal scene descriptor is the next one up that's under evaluation. Real quick overview of the rendering techniques that we'll talk about. And I won't go too fast. Rasterization, long time, highly optimized. It operates in pixel line with pixels, lines, and object triangles, rather, mainly triangles. And all the objects go through a pipeline. And while it's getting quite a few tricks and methods for lighting, it still is estimated kind of a imperfect end result. For ray tracing, we're monitoring the physics of light. You also can intersect any geometric object, although often it is tessellated. And then, one of the things is that the methodology, the bounding volume hierarchy and KD trees allow for the visibility to happen not necessarily in depth space. And of course, it's light physics. And these give you these images, which we've used over and over, give you a sense of this is the same 3D model, but this is the type of differences that direct lighting and rasterization give you versus the nuances and deeper view and higher fidelity of ray tracing. Let me talk a little bit about our offerings, where we are with them. So last year, we branded our package of offerings into something called the One API Rendering Toolkit. This allows you to develop a variety of applications, all software-based interfaces that are open. Again, we're looking at our interface as something that continues on. The notion of One API is a cross architecture platform. And as we add our XE GPUs, they will be sort of automatically absorbed into the platform and the capability that we provide, as I was talking before. You know, the usages, we've talked about that wide range of usages earlier. And of course, the key benefits are, you know, we can deliver scalable, high performance, the highest fidelity images, various global illumination capabilities that we continue to grow. We can work on any compute infrastructure that has SSE and beyond. We auto detect the vector and parallel capability, so you don't have to worry about that. We will maximize the performance. Real quickly, the 5 key libraries: Intel Embry, again a core geometric rendering capability. Intel. Let me jump to volume kernel library. Actually, volume kernel library is something relatively new, but it's very, very cool. You can do 3D spatial computing, as well as supports various volume rendering, clouds, scientific data. It is a very powerful tool. Then Open Image Denoise is our AI denoiser. We'll talk about all these a little bit more. Open Swir is our rasterized engine that turns any CPU into an OpenGL renderer, and with upstream to Mesa, so it's available as part of the Mesa package. And then Intel Osprey brings it all together. Let's talk a little bit more about a couple things coming soon, and I think they're actually available on, some of them available on GitHub in their early stages, but we are working on something called Osprey Studio. It's actually a what I call a hello rendering application. It's way more than Hello World, but it gives you access to the full breadth of and the capabilities of Osprey in a best use type application. It will allow you to visualize and render various things. Again, the Bentleys you see there are with a pre-release version of Osprey Studio. And then we have HD Osprey. We will continue to grow this. This is for the universal screen description that is heavily being adopted as an open source interoperable environment for film and television rendering. And they have an interface called Hydra. That's where the HD comes from within there, and it's in particularly good at interactive viewport capability. Real quick, usage, the types of usage that people can do in professional rendering. They're using Embry and Open Image Denoise today, and there are several in-process developments adding Open Volume Kernel Library, volume rendering in film for clouds, explosions, things like that, is really rapidly growing. So soon you'll see Open Volume Kernel Library on this, particularly Blender is using that. But this is some of our workflows and customers here using professional rendering and some of the great stuff that can be generated. Scientific visualization kind of brings all the packages together with almost every library and capability we have. ParaView is the premier example of taking everything we have and utilizing it and improving your visualizations. Visit as well. And then you have others that are raster or OpenGL focused, but work work scalably with Intel OpenSWR. And then we have a few others like Megamol from Visus at Stuttgart, University of Stuttgart, who have dropped the rasterization part and have gone full-blown Osprey, which of course underneath Osprey has Embry, OpenVKL, and OpenImage Denoise again. And as we move to Inari, you will see that that continue to be one of the key mechanisms to access our kernel libraries. I'm just going to give you some eye candy. Why not? This is a gallery. This is, again, How to Train Your Dragon Hidden World by DreamWorks. Fantastic view here from their Moonray renderer, which is built on top of Embry from the ground up. Really cool shot from Spider-Man Far From Home, this scene developed by Framestore in conjunction with Sony Pictures. I just saw this the other day. I can't stop watching it, and this is a great scene in the movie. For more fun, Lego Movie, Animal Logic has utilized Embry for many years in their glimpse renderer. Chaos Group's V-Ray is heavily used in conjunction with Maya. We actually had it on the professional rendering setup screen there. And here are some past movies as well as the famous Thanos character rendered in the Avengers movies, rendered from Maya with a V-Ray plugin based on Embry. This is stellar radiation. Again, I'll give you a video of this, just a larger screen from UC Santa Barbara and Joe Inslee and Silvio over in Narcon National Labs. This is somewhat hot off the presses, developed for I guess, now defunct, I'm not sure, Dome rendering for Euroviz. A little bit hard to see, but this is Africa with Lake Victoria. This is from DKRZ and Nicholas Robert. And this is, when you see this animated, it's really, really cool. But this is a new weather and climate app. And this is rendered with ParaView and a pre-release of ParaView with Osprey 2. Our latest Osprey version, and very cool if you see the reflections and things like that. So thanks to Nicholas and the team. It's been a great collaboration. We are working closely, again, fairly hot off the presses with Bentley on a virtual experience using their manufacturing models. So these are the models, 3D models that they use in all their design tools, and we have incorporated them into Osprey, utilizing Osprey Studio and getting some pretty spectacular things. So many thanks to Bentley Motors Limited for the models and the collaboration here, and just can't get enough of them. This is extremely cool scene, and you'll see that this is a screen capture. So this is Osprey running. Or Osprey Studio actually running over here, backed by Osprey. This is the 3D model here, the silver model. These renderings done by Bruce Cherniak on my team. Again, cool background here, as if you're in the showroom. Reflections off of the roof of the car. This is actually meant to mimic a video monitor in the showroom, and there is a real showroom that looks like this, but this is a rendering of it. And then this literally is from yesterday, taking the San Miguel scene, both public San Miguel scene plus the public blower model, integrating the two together, and just even we like to have fun sometimes instead of just working. So we thought it'd be fun to put this up. With the headlights are kind of lightly on there, and the cool reflection and glow of the fountain is just spectacular. Again, all rendered, not a photograph. I'm going to kind of breeze through this, but I've already told you, we've got a number of partners and success stories from chaos groups, not only V-Ray, but Corona Renderer, all based on Embry. Studio workflows like Moonray. You'll see lots of stuff from us working hand in hand with the Stephen Hawking Center for Theoretical Cosmology, lots of gravitational and gravitational wave work. We have great customers and partners. You don't have to, you can read this later. Xavier has been a real contributor to all our libraries. Embry, he's giving feedback on OpenVKL and OpenImage Denoise. At Illumination, Secret Life of Pets 2, The Grinch movie, Service Engineering, another close partner in the DoD space, and Maxon Cinema 4D. Make you aware that we have Intel Graphics and Visualization Institutes of Excellence. We call them Intel GVIs. So many of our friends out there that look at who the PIs are. Feel free to reach out to them or me with some of the groundbreaking research they're doing in conjunction with us and moving the whole state of the art forward. One of the really strong benefits of having open source is we can have these great partners contribute not only applications but directly to our libraries and give us advanced feedback on their usage. So many thanks to all of these folks. And if you need more resources, we've been really updating lately. I hope you've seen our webpage. It's software.intel.com /1API-rendering-toolkit. It was on the front. You can see where it is, and I believe it's linked. It'll be linked against this. So, So I think I'll stop there. Hopefully I didn't go too much over time, and happy to answer some questions. So back to you, Felicia.
Thank you so much, Jim. I just want to mention that the other keynote has started, Kavita Bala, but I think that we could have time for one or two short questions. So this was a great presentation. We've seen a bit about what's at the front edge at Intel's. Could you tell me a little bit about what are the limitations and what you think will be the next thing? What will be in the future?
Sure. The limitations, I guess I'll boldly say the limitation is your imagination, right, for using our tools. But mainly your limitation, if you want to call them limitations, is for us is the full platform, the full memory, the full capability, what you have access to. And this is where we talk about scalability. So the in one sense, your main limitations are for getting high quality rendering are your memory footprint. Complexity generally equals size, so that and then if you have to move the data around once you have it. Also, loading large data is actually a really difficult thing. There are techniques that Intel is continuing to promote to do that, but I/O is a real challenge, PCIe I/O or other I/O. But our tools, the scalability of our tools, really try to minimize that with our distributed rendering capability that lets you scale up to thousands of nodes if you want, stick on one dual socket workstation, or even many people, including our own team, run on their laptops. Again, so kind of your limitation really ends up being what are the platforms available to you, and if you begin to run into problems, you can do things like work with Paul Navratil at TAC or other venues. And the beauty is Osprey, as I said, you can play around, with lower quality on your laptop, or you can get access to a supercomputer like LRZ or at LRZ Supermove or TAC and break through those limitations.
Thank you. Matteo Vespo is asking on YouTube, if render is based on Osprey, what effort would it be to use one API?
So that's interesting. It's difficult because I have a perspective. One API is kind of a promise, right? So it depends on really what you're asking. One API is a promise that sort of like our Intel's promises of supporting legacy code in the past. One API is a forward-looking promise that as we add capabilities like our XE architecture GPUs, FPGAs, that your ability to use the code use code across those platforms, either individually or conjunction, as I was talking about, is we are doing everything to enable that through our variety of tools that have existed and that we're mapping to those architectures, like Math Kernel Library. And then, of course, we are looking at programming tools like Data Parallel C++ based on SYCL, as well as maintaining our ISPC platform, which we use fairly heavily in our development. These all will move cross-platform over time. So hopefully that answers the question, but one API is a set, a reference specification, an implementation by Intel that we believe will help you maintain portability across the varied compute devices that can help you get your job done.
Thank you so much. And thank you again for a wonderful presentation. I hope to hear more from you soon because this was interesting.
Thanks so much, Felicia. Appreciate the extra time also. Thank you.
No problem.
Stay safe, everyone. Bye-bye.
Bye.